Okay. Okay, so it's nice to see some of you here. As I said, I will not be able to take the live class on Friday, like means this like day after tomorrow, due to a research related engagement. Therefore, I'm recording this lecture and it's good to see some of you. So yeah, let's have it like a live class. Okay, so we have been discussing this topic of deadlocks and uh, maybe a 3 minute to 3-4 minute recap. So we have understood what deadlock is, and we have formally almost defined it as in deadlock can arise if these four conditions hold simultaneously. So there should be some processes waiting for some other processes, and those processes in turn waiting for other processes who are also waiting for others and so on. So basically there exists a set of processes such that every process in this set is waiting for some event which can only be caused by some other process of this set only. Okay, so basically they keep on waiting forever because no, like that process for which, I mean that process for which one process, a PI, is waiting, that process is itself waiting for some other process and so on. Then we discussed another way of characterizing deadlocks, which is through a graph. So this kind of a graph we discussed, that these circles are the processes and these rectangles are different resource types, and these small circles, small dots, they are actually resource instances. So a particular resource type can have only one instance, like say R1 and R3 here, or a particular resource type can have many instances, like R2 has 2 instances, R4 has 3 instances. And we discuss these edges. That means when a process is waiting for a resource, then we put an edge from the process to the resource, like P1 is waiting for an instance of type R1. So this is a request edge. The other edge is an allocation edge. So here this instance of R1 has been allocated to P2. Right, so this is how we discuss this graph, the resource allocation graph, and we understood that the presence of a cycle in this graph may indicate a deadlock. Right, so it's not essential. So it's, you might say it's a necessary condition, but not a sufficient one. Okay, so yeah, if the graph contains no cycles, then there is no deadlock. If the graph contains a cycle, there is possibility of a deadlock, but there is no guarantee. Yes, one guarantee is there. If only one instance per resource type, then a cycle becomes a sufficient condition for a deadlock also. But if there are several instances per resource type, then it cannot be said that a cycle in the resource allocation graph directly indicates a deadlock. Okay, so this is how we have characterized deadlocks. Now we have come to handling deadlocks. That is our main point of discussion for today. And we ended with this slide where we said that, so basically there are three broad approaches of handling deadlocks. One is that ensure that the system will never enter a deadlock state. This is usually called deadlock prevention and avoidance, which we will discuss today. The other is, okay, even let a deadlock happen, but then detect it and then do something to resolve it. This is called deadlock detection and resolution. And the final thing is to completely ignore the problem of deadlocks, pretend that it never occurs. And surprisingly, this is what is used by most operating systems, including Linux or Unix. This is because deadlocks are rare, and more importantly, as we will discuss these methods today, like deadlock prevention, avoidance, and all, we will understand that they are very complex methods, or like costly or expensive methods. There are algorithms, but if you actually have to use such algorithms time and again, like say you have an algorithm for deadlock detection, but you have to run it ever so frequently to detect if there is a deadlock. So doing this will actually create more pressure on the system because this algorithm will also use several resources and so on. So what OS designers have found is it's best to ignore the problem and pretend that deadlocks never occur. If it happens at some point that some processes get into a deadlock, then the human beings using those processes will get impatient and some of them will simply kill their processes. That is the standard assumption. Okay, so let us now actually discuss some methods of, let's start with deadlock prevention. So here the basic idea is what is written in blue here. So basic idea is, so you remember we had discussed 4 necessary conditions for deadlock. Those 4 have to be valid if a deadlock has to exist. So here the main idea is ensure that at least one of these necessary conditions do not hold or cannot hold. Okay, that is the basic idea. And how to do it? Basically, impose some restrictions on how processes can request for resources. Okay, let's see. So what are some standard ways of ensuring that mutual exclusion cannot happen? Okay, this can be only partial because some resources are shareable, like a read-only file and so on. But then by definition, some resources are not shareable. Therefore, if you have a set of processes which try to access a non-shareable resource, then you cannot say that I will, disable mutual exclusion. That's not feasible. However, of course, if resources are shareable, then you should not impose mutual exclusion on those resources. Next is hold and wait. So remember, this is what we want to prevent. So we want to prevent the hold and wait condition. So how? There are 2 very intuitive methods. Say a process blocking on a request should not be permitted to hold any resource. So actually some of you had mentioned this point in the last class, that suppose the process is holding some resource R1. Now it is requesting for another resource R2. The OS figures out that R2 cannot be allocated right now. So then this process must be blocked. So then why even allow it to continue holding R1? Rather free it, like the free R1, so that it can be used by some other process. The second variant is a process holding a resource should not be permitted to make additional requests. But this seems a bit bad because maybe the process has been reading till now it will write. So how can that happen? So basically a simple and practical approach is that require a process to request and be allocated all of its required resources before it begins execution. Okay. This is a simple scheme that it makes a rule that in this system, every process before it begins execution has to list all the required resources. Okay. So it's a simple approach, but the problem is it will lead to low resource utilization. Why do you think there is this problem? So why do you think this simple approach written on this slide can cause low resource utilization? Yes, Shubham, resources will sit idle, but why? Yeah, okay. So Ayush has a better answer. I guess Shubham was also trying to say the same thing, but yes. So exactly what Shrihas, Ayush, they have pointed out. So maybe a process needs to do a lot of operations and then write a small piece of like text to somewhere. Now, if it right from the beginning, if it continues to reserve, say, the printer or some file to which it needs to write the information, then throughout the process, throughout the time when it was doing computations, this resource will become blocked, right? So that's not an ideal scenario. Resources are costly, therefore we want them to be shared as much as possible. Therefore, allocating resources to the process throughout its lifetime is not a very good option. Okay. Let's proceed to other ways of deadlock prevention, and we are again going ahead with the same idea that we will prevent the necessary conditions for a deadlock to all of them for existing. We will ensure that all the necessary conditions for deadlock cannot become true. The another necessary condition for deadlock was no preemption. We can prevent that or we can disable that. How? Let's say the OS makes this rule that if a process that is holding some resources requests for another resource that cannot be immediately allocated to it, that means this process has to be blocked, then all resources currently being held by this process are released. And all these released processes, which are called preempted, all these released resources, which are called preempted resources, are added to the list of available resources so that other processes can use them. Also, for this particular process, which is being put on hold, later when it resumes, it will need back these resources, these preempted resources. Therefore, these preempted resources are added to the list of resources for which the process is waiting. So possibly this process will be resumed at a time when all these resources for which it is waiting are available. That's what's written. Right. And finally, so these are some standard ways of preventing this no preemption condition. And finally, the circular wait condition. Remember the condition that we said there has to be a circular set of, a set of processes where there is kind of a cycle that say P1 is waiting for R1. R1 is being used by P2. So essentially P1 is waiting for P2. Again, say P2 is waiting for P3. P3 is waiting for P4 and back, like P4 is again waiting for P1. So we do not want this kind of a circular wait. So again, there can be several ways. One simple way is impose a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. Right, so it can never happen, let's say, that P4 is waiting for P0, let's say. So, okay, P0 can wait for P1, P1 can wait for P2, P2 can wait for P3 and so on. But the final cycle will never be completed, as in P4 will not wait for, say, P0 or P1 or P2 or P3. Okay, so we somehow break that cycle, this hold and wait cycle. Okay, so these are some standard methods for deadlock prevention. Now we will go ahead to deadlock avoidance. Before that, any question? Okay, if not, fine. Yeah, I think these are simple things. So fine, let's go ahead to deadlock avoidance. Okay, Shubhami has a question. Can you give some examples of resources that can be preempted? Okay. Again, just from the top of my head, in certain conditions, maybe semaphores can be preempted. Let's say that before entering a critical section, a process has to wait on two semaphores. We have seen such examples in the previous chapter. Let's say it is able to get hold of one semaphore, but it is not yet. So it requests or waits for the other semaphore, but it is not yet allocated. It does not yet get that semaphore. So then it's evident that the process has not started its critical section and it has to wait. So then that semaphore which it had already got can be actually freed up. Okay, that's just one example. If anyone else has some other example in mind, please share it here. Or maybe two files, like, yeah, it wants to, so this process wants to, so there are two files, so both are read and write files. So a particular process wants to read from one file and write to another file. So maybe it has gotten access to the read file that it wants to read from, but it does not yet have access to the other file which it wants to write to. So it has to wait. Therefore, even that file from which it wanted to read, that is also actually a read-write file. Some other process may want to write there. So maybe that file is also preempted from it. So when this process will be resumed when both these files are available. Okay. Okay, so let's proceed then. Yeah, deadlock avoidance. So remember that in deadlock prevention, our main idea was that we want to prevent at least one of those necessary conditions for deadlock. Okay, now let's see deadlock avoidance. The deadlock avoidance does something different. The goal is the same, that is to prevent deadlocks from occurring, but the approach is different. Deadlock avoidance, let me just explain the idea, then I can go to the slide. So every time a process, okay, so deadlock avoidance we will see has some ways of identifying whether a system is in a safe state or an unsafe state. What is a state here? A state is defined by the resource allocation right now and how many other resources different processes would need. We will formalize these. I'm just giving the idea. So think of a state diagram kind of thing. A state consists of all such information like which resource is allocated to which process right now, how many processes are there in the system, which process can request for how many additional resources, and so on. So that's the whole resource allocation state of the system. Deadlock avoidance algorithms have some way of identifying whether a resource allocation state is safe or unsafe. We will define what safe means, unsafe means. The idea is that every time, so given the current state, let's say the system is currently in a safe state. A particular process requests for a resource. Now, there can be two options. One is the resource is not available. In that case, the process definitely has to wait. Second case is the resource is available. So now the key question is, should the OS allocate this resource immediately to the requesting process? Or should the process be made to wait? This depends on whether the state, okay, this depends on the following. This decision depends on the following. If this resource is allocated to the process, then does that change state also remain safe? If yes, then the OS will allocate this resource immediately. However, if allocating this process right now can cause the system to go to an unsafe state, then the OS will not allocate this resource immediately. Rather, the process will be asked to wait. Okay. So this is the broad idea. So now, of course, there is a big assumption here that the system has some additional a priori information about the resource usage patterns of the processes. Okay, this is an assumption. The system, in order to run such deadlock avoidance algorithms, the system has to have some a priori information about the resource usage patterns of the processes. And the simplest idea is that the OS requires that each process declares the maximum number of resources of each type that it may need. Each process declares the maximum number of resources of each type that it may need. Okay. And before allocating a resource, as I was explaining, the OS checks whether this allocation may lead to a potential deadlock situation in future. Right? Okay, now we will discuss this, but before that I have a question. So focus on this. So basically the OS says that every process has to declare, before starting, let's say, every process has to declare the maximum number of resources of each type that it may need. So let's say, does that mean, okay, let's say I am writing such a process. I'm writing a program and say I have to declare how many processes, sorry, how many instances of which resource I need. So would it not be safe just to say that I need maximum number of resources of each type? Maybe I know that in the system there are 5 instances of resource 1, 6 instances of resource 2, 3 instances of resource 3, and so on. The simplest idea would be I say that I need all these resources. I need 5 instances of R1, 6 instances of R2, 3 instances of R3. Why would or should I do it? Or if not, why do you think I should not do it? Okay, Sriharsh said would lead to underutilization. Very good answer, but I don't care. I want my resource. I want to simplify my job. Why do I care about utilization of resources? For me, the simplest way to write my program would be I say I need all these resources. Maximum number of resources I need is whatever is available of each resource type. I don't care about underutilization of resources. Of course, I'm a selfish programmer, but let's say that way. Is there any reason why I should not behave like this? Yes, Shubham, if everyone does this, then running the algorithm will have no effect. Agreed. My question is, why should everyone not do this? Just an intuitive answer. Maybe some of you have heard of, at least even if you have not studied, maybe all of you have heard of something called game theory. Right. So there, like people play games, and then, I mean, games do not mean like cricket or football, but some specific types of games where it's kind of a puzzle kind of thing where there is some condition which ensures that cooperating with others is the best possible way. Right? So if everyone starts behaving selfishly, actually everyone will be harmed. Right? The best interest of everyone is to cooperate. So such theories are discussed in game theory and so on. But okay, that's just a digression. In this particular scenario, can you think why everyone should not behave selfishly and just say that everyone needs the I mean, why shouldn't everyone just say I need all resources that are available? Okay. Dhrumil says as resource allocation state is defined by number of available resources, sometimes safe can be marked as unsafe. Okay, Dhrumil, again, what you are telling is not wrong, but that does not answer my question as to like why should I care whether the state is safe, unsafe, etc. Okay, Radhika is possibly going towards the correct answer. So Radhika, can you just unmute yourself for a minute? What do you mean process may starve?
Sir, since my process has a maximum requirement of all the resources, so it may happen that at no point I'm getting all the resources.
Exactly,
So my process may starve actually.
exactly. That's the idea. So if I just say that I need all available resources, as a programmer, my job would be simpler perhaps. But then I have to be prepared that my process will be allocated or my process will be allocated all these resources maybe much later. I mean, we will discuss some algorithms. So then, but keep this idea in mind that if I say that my process needs lots of resources, then the chance of my process actually being allocated all those resources will go on reducing. So maybe my job as a programmer would be simpler, but then my process will take a lot of time to run because the OS will not be much willing to allocate my process. I mean, allocate so many resources to my process. Right, this is just an intuitive idea, but understand that this, unless there is this trade-off, everyone will start behaving selfishly. Right. So again, I'm not discussing those things here. If ever you do a course on some things like game theory, then you will maybe understand or appreciate this more clearly, that usually such games ensure that uh, cooperating with everyone is your best way forward. I mean, that applies for everyone. Okay. Okay. Yeah. Okay. Let's go on. So let's now actually formalize these things. We are telling many terms like resource allocation state, safe, unsafe. Let's start formalizing them. So basically, a resource allocation state is defined, and it is defined by the number of available and allocated resources, maximum demands of the processes, how many resources the processes have already got versus how many are still pending. All these things make up the resource allocation state. Now a state may be safe or unsafe, right? When a process requests an available resource, decide if immediate allocation will leave the system in a safe state. This is what I was explaining. When a process is asking for a resource, decide if the OS has to decide if it should immediately allocate that resource to the process. And it will do so only if, even after allocation, the system remains in a safe state. Okay. The next slide will define what a safe state is. Before that, I just want to hear your intuition. What do you think a safe state would be? When would a state be safe? Again, I am not asking for any formal answer, just intuitively. When do you think? So suppose there are n processes in the system. Every process has some resources allocated to it, etc., etc. It wants more resources. Very intuitively, what do you think would be the concept of a safe state? No, okay, Radhika, no two processes require same resource is like impractical, as in it can always happen, right? There are n processes and n is quite large, right? Okay, Srihash's answer is more feasible, no circular weight. Can you formalize that a bit more? So Srihash, you might unmute yourself for a minute.
Yes, sir. So basically, if a process is holding a resource and another process requests for that resource, we shouldn't, we would consider it to be unsafe.
Wait. No. See again, wait. As I said, suppose there is only one instance of a resource R1. Then if one process is already holding it, of course, there is no question of allocating it to someone else. So that's not the idea. The thing is, there is, let's say, some free instances of a resource. Even then, whether it would be allocated right now or not, that is what we are saying. So, okay, so Srihash is saying no circular weight. Shubham is saying no cycle in the resource allocation graph. Fine, but again, okay, fine. The particular algorithm that we will discuss actually does not use the resource allocation graph, though it can be used, fine. Okay, but I was just thinking, what do you mean no circular weight or no cycle? Can like either Srihash or Shubham, can you just a bit more formalism, as in what are we looking for? When would we call the state safe? You are in the right direction, no cycle, but what of it? Maybe Shubham, you can unmute yourself and.
Sir, I mean that even if there is a cycle, then all the nodes in the cycle will have some free instances of the resources available. Then only we can call it safe. If there are no free instances along that path, then it is unsafe.
Think a bit more deeply. Is it absolutely essential that there should be free instances? Maybe at this point, no resource is free. Does that always mean that the state is unsafe? Think a bit more deeply. This is the key point of the algorithm that we are going to discuss. Suppose at this point none of the resources are free. Does it immediately mean that there is a deadlock? Exactly what Ayush is saying. Some processes can finish and free up resource instances. So maybe at right now there is no free resource, but then some process can finish and free up resource instances. Again, see, this is a conceptual point. Just because all resources, I mean, none of the resources are free now, does not immediately indicate there is a deadlock. Some process can finish and free up resource instances, which can then be utilized by other resources and so other processes and so on. So now, can some better answer, like, when do you think a process state is safe? Okay, let me clarify. What all you said are not completely wrong. As in, suppose there is enough free instance of every resource, then the state is safe. Okay, sure. But then even if resources are not free, even then the state can be safe. If a condition holds, what is that condition? Something which Ayush pointed out in that line. Maybe Ayush, just unmute yourself and maybe you just.
If no other resource instance is required by some process, so it can perform execution.
Yes. And so suppose there is a process which does not require any more resources. It has got all the resources that it requires. So this can finish.
Yes.
And free up its instances. Then,
yes.
Then just go forward one line. So these freed up resource instances may enable another process to finish. Right, so maybe there was one process which had got all the resources allocated to it. It does not require any more resource. So eventually it will finish. That will free up some resources. Using those freed up resources, maybe some other process can finish, and so on. Right? So basically, if such a sequence of processes exists, that at least the first one can finish, after that first one finishes, the second one can finish with the resources freed up by the first one. After 1 and 2 finishes, the third process can finish with all the resources freed up by 1 and 2. As long as such a sequence exists, the state is safe. Is it okay? Let me repeat, even said at this current point of time, no resource is free. All resources are allocated. Even then, there is such a even then, if there is such a sequence as I just described, then the system is in a safe state. Do you agree, or do you have any questions or doubts? By the way, these algorithms assume that suddenly no new process will come up, etc. So we know this set of processes. These are the processes. So is this clear, or do you have any doubts? Okay, let's formalize this. I think it will be clear. So basically, a state is safe if the system can allocate resources to each process in some order and still avoid a deadlock. So more formally, suppose there exists a sequence, a P1, P2 up to Pn of all processes in the system, such that for each PI, the resources that PI can still request, I mean, in addition to what it has already now, can be satisfied by currently available resources plus resources held by all the Pj with j less than I. This will be a small I, sorry. As long as such a sequence exists, the state is safe. And this such a sequence is called a safe sequence. Right? And the reason is written in the lower part of this slide. Right? So basically, even if PI resource needs are not immediately available, PI can wait until all Pj with j less than I have finished. And once that happens, like all Pj with j less than I finishes, then P1 can obtain all the resources that it needs, and then it can finish. And once Pi terminates, Pi plus 1 can obtain its needed resources and so on. So basically by induction, all processes will terminate. Right? So this is what I was trying to get at. Some of you reached quite close to that answer. So basically, if there is a safe sequence, then the system is in a safe state, even if no resource is free right now. Okay. So basically now, if the system is in a safe state, then there is no possibility of a deadlock. If a system goes in the unsafe state, then there is a possibility of deadlock. Though it cannot be guaranteed always that there will be a deadlock, but there is a possibility. However, deadlock avoidance algorithms do not take that risk. They ensure that a system will never enter an unsafe state. Okay, Rashil has a question. Sir, this sum order is bound. Okay, this sum order means, okay, yes, this one is bound to affect scheduling order, right? Yes, but like, so what's the point? Because of course here, say in this, what is written in this slide according to this, there is no point in scheduling Pi before all Pj with j less than I have finished. Because Pi will always be waiting. I mean, until that happens, that all Pj with j less than I finishes, until that happens, Pi will be blocked, as in it is still waiting for some resource which it is not, which is not available. So of course it will affect scheduling order. But yeah, but do you have any follow-up question, or is this okay? Fine. Okay, so this is the idea. So basically, let's understand that the picture is like this. Every unsafe state does not necessarily mean a deadlock. So a deadlock is a sub part of the unsafe state, like the universe of unsafe states. But then the algorithm will not take that chance. The algorithm that we will discuss actually ensures that the system always remains in the safe state. Okay. So now, let's go ahead with an example. Let's say this is the state right now. So you have these 3 processes, and in total we have 12 instances. Let's talk about only one resource type. Okay, we have 12 instances of that resource type, and there are these 3 processes. They have declared their maximum need 10, 4, 9, and current allocation is 5 to 2. Now the question is this state safe? Does there exist a safe sequence? Hey, I thought this was easy, right? Any answers? Yeah, so what is the safe sequence? Yeah, okay, Dhrumil says P1, P0, P2. It seems he is correct because see, currently 9 instances are allocated. So out of 12, 3 are still free. So then P1 will maximum request for 2 more resources. 2 more instances. So since there are still 3 free, P1 should not have any problem in completing. Once P1 completes, 4 instances will be available. So then using that, when P1 completes, then how many resource instances will be available? These 4 which it will free up, and the 3 are still which are still remaining. So 7 are remaining. 7 are free at that point when P1 has terminated. These 7 can be allocated to P2 and it can complete. After that, P0 can complete. So Dhrumil, okay, I think it will be P1, P2, P0, right? Or okay, I think both are okay. Like P1, P0, P2 is also possible, and I think P1, P2, P0 is also okay. No. Yeah, I think what Dhrumil said, that is more. Yeah, I agree. Yeah, what Dhrumil said previously, P1, P0, P2, that is more likely because P2 can still ask for 7, right? So that's, I mean, that might get stuck. So yeah, right. So after P1 completes, the number of resource instances that remain are current 3 which are free and these 2 which are currently allocated. So 5. So after P1 completes, 5 instances of the resource would be free. Those 5 can be allocated to P0, which can then finish, and finally P2 can finish. So there exists a safe sequence P1, P0, P2. Okay. Yeah. So good. Now let's see. The second thing is, now let's say given this state, so this was the state which we know it's a safe state because there exists a safe sequence. Now say P2 requests one more resource. P2 requests one more resource. And let's say it is allocated that. So from 2 now it becomes 3. Now think about it. The system state is no longer safe. And the reason is given here. Because again, that's the thing. So as we discussed, P1 can still finish, but then that will free up 5 resources in the previous slide, like when the state was safe. Now if P2 is allocated 1 resource, that means even after P1 ends, we will have only 4 resources. There are 2 which remains and these 2. And that is not sufficient to complete either P0 or P2. So then the system is in an unsafe state. So then according to the algorithms which we are going to discuss, this request from P2 should be denied. That means P2 should not be allocated 1 more resource right now. It should be made to wait. Okay, is this clear? Okay, so now the question is, what kind of an algorithm will help in deciding all these things? So I think we have got the basic idea, but then what algorithm should be run? So there are 2 variants of algorithms. One is using a resource allocation graph. But this is feasible only when there is a single instance of a resource type. However, when there are multiple instances of a resource type, there exists another algorithm for deadlock avoidance that is called Banker's algorithm. That's quite popular, and that is what we will study. Right? So I think, take it as a small task to figure out how this case can be figured out. This should be quite easy. Some of you might already see, because we have discussed about cycles and so on. but let us discuss this new thing, the Banker's algorithm, which can handle multiple instances of a resource type. So Banker's algorithm assumes this, that there are multiple instances of a resource type and each process must declare the maximum resource requirement a priori. Right. So also the constraints are that when a process requests for a resource, it may be denied even if the resource is available. Right, as we discussed in the previous example. And also there is this tacit assumption that when a process gets all its resources, it must return them in a finite amount of time. Like a process should not try to hold some resource for infinite time and so on, right? Okay. So now the Banker's algorithm considers these arrays or vectors, if you think. Actually, the algorithm is quite simple, but yeah, it uses lots of data structures and vectors. So there is this vector, okay, let n be the number of processes and m be the number of resource types. There is this vector available which stores how many instances of which resource type is available. Okay. Max is the maximum allocation, the maximum demand of a process. Right. So this is an n cross m matrix because every process has to say how many instances of which resource type it can ask for at maximum. Right. So this is going back to that assumption of Banker's algorithm that every process must declare a priori how many instances of which resource it can ask for. That is stored in max and matrix, n cross m matrix. Similarly, there is another to n cross m matrix called allocation. This is keeping track of actually how many instances of which resource type is currently allocated to which process. Okay. And there is this need matrix, which is basically max minus allocation. So how many more instances of a particular resource type can a certain resource still need? Okay. I think this is simple. If you have any question, you ask. So now just two notations. If x and y are vectors of length n, then we say x less than or equal to y if and only if every element of x is less than the corresponding element of y. Right. And finally, we denote a particular row of the matrix as a vector. So allocation I, this is the vector which says, which basically considers the resources currently allocated to process Pi. Similarly, need I vector is stores the additional resources that process Pi may still request. Okay. So this is what the notations which Banker's algorithm uses. Okay, so let's see. After this, we have the algorithm. But yeah, I think, let's not start the algorithm today because it will take some time and it's already 55 minutes. So let's stop here. We will discuss the main algorithm tomorrow and finish up this topic. So at this point, any question? Okay, fine. So thanks to all of you who attended. Let's end this class. We'll continue tomorrow.